So the thing is, when you want to build something great, it's not easy to do. And when you're doing something that's not easy to do, you're not always enjoying it. I don't love every day of my job. I don't think every day brings me joy, nor does joy have to be the definition of a good day. And every day I'm not happy. Every year I'm not happy about the company. But I love the company every single second. And so I think that what people misunderstand is somehow the best jobs are the one that brings you happiness all the time. I don't think that that's right. You have to suffer, you have to struggle, you have to endeavor, you have to do those hard things and work through it in order to really appreciate what you've done. And there are no such thing that are great that was easy to do. And so by definition, I would say, therefore, um, uh, I wish upon you greatness, which by my way of saying it, I wish upon you plenty of pain and suffering. And so the thing is, when you
Testing. So we wait. Salary to our
Everyone see the screen? You need to close light on. Okay. Some the mic here very sensitive. Maybe watch some video first. Motivating video. Wake you up before we start. This guy is very I like his talking. He's very logical. He's the NVIDIA CEO. You like NVIDIA or not? You buy computer or not? You buy laptop or not? The NVIDIA graphic card. Okay, but his company is now creating AI chips. AI chips for these open AI to build the super computer to run these ChatGPT something like that. And his stock like double up from like maybe 300 USD until 1,400 now. Just within 1 year. So you missed the train. Okay. Let's see what he said.
Build something great. It's not easy to do. And when you're doing something that's not easy to do, you're not always enjoying it. I don't love every day of my job. I don't think every day brings me joy, nor does joy have to be the definition of a good day. And every day I'm not happy. Every year I'm not happy about the company. But I love the company every single second. And so I think that what people misunderstand is somehow the best jobs are the one that brings you happiness all the time. I don't think that that's right. You have to suffer. You have to struggle. You have to endeavor. You have to do those hard things and work through it in order to really appreciate what you've done. And there are no such things that are great that was easy to do. And so by definition, I would say, therefore, I wish upon you greatness, which by my way of saying it, I wish upon you plenty of pain and suffering. And so the thing is, when you want to build something great.
Are you suffering now? It's okay to suffer, but what did he say? Maybe when you do max, you cry, but you have to love it. Love it. Okay. How many times he said definition? But definition, therefore, is it these are logical person, right? Very logical. There's one more to share before we start. You can go and watch his presentation. Very clear one. Even you don't know about computer science, you can follow what he says. Okay, you go and follow his like keynote speech in the conference. You can find YouTube. Very clear. Okay, you understand the flow. Okay, even though you don't know what chips is that, what AI stuff, but you still can follow his speech. It's very good.
One of my great advantages is that I have very low expectations, and I mean that. Most of the Stanford graduates have very high expectations, and you deserve to have high expectations because you came from a great school. You were very successful. You're top of your class. Obviously, you were able to pay for tuition, and then you're graduating from one of the finest institutions on the planet. You're surrounded by other kids that are just incredible. You naturally have very high expectations. People with very high expectations have very low resilience. And unfortunately, resilience matters in success. I don't know how to teach it to you, except for I hope suffering happens to you. And I was fortunate that I grew up with my parents providing a condition for us to be successful on the one hand, but there were plenty of opportunities for setbacks and suffering. And to this day, I use the phrase pain and suffering inside our company with great glee. And the reason, and I mean that, boy, this is going to cause a lot of pain and suffering. And I mean that in a happy way, because you want to train, you want to refine the character of your company. You want greatness out of them. And greatness is not intelligence. Greatness comes from character. Character isn't formed out of smart people. It's formed out of people who suffered. And so that's it. And so if I could wish upon you, I don't know how to do it. For all of you Stanford students, I wish upon you ample doses of pain and suffering. One of
Hello.
So his famous phrase is, "I wish you a pain and suffering." Usually you wish people happier, but he wishes pain and suffering. But pain and suffering is what we met daily. Okay. So he mentioned about this low resilience. You know what's low resilience mean? low resilience，抗压性。OK， so 很长时候，可能这一代是不是这一代呢？这一代的人都被称作什么？草莓族 ，strawberry generation。Why is it strawberry？ 一折就断是吗 ？Easy to get defeated. So you need to train yourself. Okay, get overcome problems. Okay. Yeah. You can cry, but please come back after you cry. Okay, but don't just give up. Okay. Now, if you have friends, you can ask them to come. Yeah. Right. So let's start. Okay. So today we're gonna talk about the correspondence theorem. If you can't see, please let me know. Otherwise, please move to the front, easier to see. Hey, why the door is open? All right, so same picture. Okay, same picture here. We're still interested with homomorphism. Okay, we're still interested in homomorphism. Okay, let's use this notation. Here is a homo. Okay, so the picture is you have a group G. Okay, map to us. Codomain script G. Using a homomorphism. So let's say we take our kernel. We have our kernel. Let's call it K. And we know that kernel is a what? It's a subset of a group. In particular, it is a subgroup. Okay. Whenever you have a subgroup, what can you do? You can use it to partition your group. Okay, you can partition your group. So you should imagine your subgroup as a knife, right? So you can partition your, say, all right. But so how about make more people here? So let's make more one here. Maybe make 8 of them. 8 of them. Okay, let's make 8 of them. CK, EK, EK, FK, and HK. But what did we prove last time? To prove that the number of coset, right? The number of coset is equal to what? The cardinality of the image of G. Okay, so meaning you can look at the image of phi here. What happens? Let's say we got phi A, and then we got AD, and then we got phi, and PC, right? And then VD, VE, V, yeah, and also V, H. Okay. Okay, so these are the relation between elements and the pre-image here. The other word in textbook, I think they call it fiber. Okay, if you see it in the book, they call pre-image fiber also. So let me put here. So fiber is also referring to pre-image. So how do you think of fiber? Maybe you can think of it like one point with a line like that. Fiber. Fiber is what? 纤维. Okay. Yeah. So because you have a one point here, right? But there's more. Maybe there's more pre-image here. Okay. So these are the fiber. Right. So today what we're gonna see is how about this point here makes friends with each other. Okay, what do you mean by makes friends with each other? Maybe they form a subgroup. Okay, how about what if I combine some of the point here together to form a subgroup? Okay, and then what can we say about the pre-image here? What do you hope for? What can you hope for? What's the reasonable thing to hope for? Let's say the images already form a subgroup. Okay, they make friends with each other, become a subgroup. What can we hope for here? Also a subgroup. Maybe they are also coming from a different group of friends. Okay, so this is why this is how we want to establish. Because last time we already established, right? If you have a subgroup in the group, if you map it across, it's still a subgroup. Image of a subgroup is still a subgroup. But now, let's say this image form a subgroup. What can you talk about the pre-image? Okay, so this is what we're gonna prove today. Right. So before doing this, so far any question? Any question? Do you have any thought about this picture here? Really? Okay. 一凡剪头发。All right. Okay, so let's continue. So let's look at some easy proposition to warm up. So let's get the same condition we had just now. And let's look at the arbitrary subgroup of Q. So there are three statements we can prove here. How to see? First, we'll see that this kernel, okay, is a subgroup of the pre-image, let's call it H, of the script H here. Okay, so this is happening. Hello, welcome back. Oh, 要死要活呀。Title. Okay. Okay. Second, if we had this subgroup script H as a normal subgroup of G, script G, then the pre-image is also a normal subgroup. Third, if turns out this map is surjective, okay, and the pre-image is a normal subgroup, then you can talk about the subgroup script H being normal. Okay, let's spend a few minutes look at these three statements here. See what are they trying to relate. Okay. So look at the first one. First one happened in domain or codomain here. Look at the story. It happens in the domain or codomain. domain, right? Okay, so first statement is everything about domain only. Okay, so what we want to establish here, we just want to establish that the kernel is always a subgroup of the pre-image of your group. Okay. Pre-image of your group in the codomain. Does it make sense or not? Think about it. Does it make sense? Make sense or not? Why it makes sense? For example, where does phi sends kernel to? Kernel, definition of kernel. To the start with identity, right? But I think we proved that pre-image of a subgroup is also a subgroup. So subgroup contains what? Identity. Okay, so if you look at the pre-image, you should contain the kernel. Okay, but we already proved that kernel form a group, form a subgroup. So it is a subgroup. Second line relate two things. Okay, if you know something about the codomain, you will know something about the domain. Okay, so well, we already know that if script hash is a subgroup of the codomain group, then the phi inverse, the pre-image must be a subgroup as well. But in this case here, we have stronger statement. We add in a condition of normal. So seems like this normality here, you can, hey, what am I writing here? This is not the same H. So this is the normal H. Okay, so to differentiate, I put everything in the codomain is a script. Okay, in the domain is a normal alphabet. Okay, so so you see the normality, you can bring it from the codomain to the domain here. Okay, so this is the power of the homomorphism. Okay, how about the third one? What's the difference between the second one and the third one? Quite similar, correct or not? About normal subgroup. But what happens? What's the difference here? The condition stop. Okay, the condition stop. Meaning what? Tree is like the converse of true. If hash is a subgroup of G, then script hash is a subgroup of script G. The condition stop. But it is not true in general. So when is it true? Only when my homomorphism is surjective. Okay, so why we need to prove? Okay, does it make sense? So meaning if I want to go backward, I need an extra condition here. Okay, so we need this extra condition to get the converse of part 2. Okay, any questions so far? Which one? Oh, right. Thank you. Okay. Yeah. So be careful. Yeah. Okay. So whenever you see G, I want you to ask yourself, this is domain or codomain. Keep asking yourself, checking. Okay. So I think first one is easy to prove because we know that the subgroup contain identity. So if you look at the pre-image, K must be a subgroup in the inverse image. But we already proved that kernel form a subgroup, so it is a subgroup inside there. Okay. So to prove that it is a subgroup, what do you need to prove? You just need to prove first it is a subset. Okay, why is this subset? Because these are all the things you map to identity. Second, why is it a subgroup? You need to prove closure, identity, element is this, inverses as this. Okay, so these we already done before. So let's look at 2. Let's look at 2. How do we prove 2? Okay, so how do we do it? What do we need to show here? So we want to show that hash is a normal subgroup of G. So what's the definition of normal again? That is, if you take any G in capital G, what you need to show, if you conjugate your H with G, it has to stay inside the subgroup. Okay, so you need to do this. What is H? H is the pre-image of script H. So this part here. Right. So what does it mean here? What does it mean by GHG inverse is inside the pre-image? The equivalent condition here. What does it mean by your pre-image is in here? So meaning if you do phi on this element here, where you lies in? You lie in the script H. Okay, so this is by definition. We can write it further. So phi of GHG inverse live in script H. Okay. This live here means what? You are equal to something inside here. Okay, you are equal to something inside here. If you are equal to something inside here, meaning what? GHG inverse is the pre-image of that thing. Maybe your engine is still warming up. So let me write here first. So there exists H1 in script H such that P of phi of GHG inverse is HI. Okay, is it clearer to see in this way here? To see that GHG inverse is the pre-image of something in H. Is it clearer? Okay, so please remember this definition here. Okay, so what? So what? What to do? So what to do? Is this true or not? Ask yourself, is this true or not? Okay, so I turn a problem. Okay, I turn a problem in. Let's draw this out. I turn a problem in G in the domain to a problem in what? In where? Codomain. But what's our assumption? Our assumption live in domain or codomain? Where's our assumption? Our assumption live in domain or codomain? Codomain, right? So now I put a problem inside codomain. So you should think of a way, can I use the assumption in codomain? Sorry, yeah, codomain or not? Okay, can we? Can we use the assumption in codomain now? You know something about this script hash, right? This script hash is what? By assumption, it is normal. What does it mean by normal? It's phi G H G inverse here. By homomorphism, it is phi G times pH times phi G inverse. But phi G inverse is what? Is the whole phi G and then taking the inverse. Does this live in script hash or not? Why? Because script hash is normal. Okay or not? So script hash is normal, you have this exact the same statement here, but you change the capital H to script hash. But now it's assumption. Assumption meaning what? If this is true for all G, it must be true for a specific G here. PG, 5G. Does it make sense? Okay or not? Okay, so we really just playing with definition of normal only. Okay. Yeah. So you need to differentiate between proving, okay, and universal quantifier and using a universal quantifier here. Okay. So we try to prove a universal quantifier in where? In the domain, but we are using, okay, the universal quantifier in the codomain. Use through the assumption we had. Does it make sense? Okay. Which part? Any question? Sorry? How does it exist Fiji? This Fiji, huh? Oh, okay. I mean, to write out properly, right? You should start with because if you want to prove a if you want to prove a for all statement here, if you learn in analysis, right? What do you need to do? You need to take arbitrary H in H, and then arbitrary G in G. Okay, that's all. So we fix one first, and then after we fix it, and then we try and compute this, and this is always true. Okay, yeah, so it works. Okay, take arbitrary H and G, and then you compute what is phi of GH inverse. So once you get this line, you go backward to this line here because we have an equivalence here. This is just the definition of inverse. So whenever you see this kind of for all, you need to fix one first, arbitrary one. Arbitrary. Okay, so this is about the normality. How about the second one? Okay, second one is similar here. Okay, second one is similar here. You want to show script hash is normal. Right, so what to do here? How about I give you 2 minutes? Yeah, 2 minutes. Try write down the proof. I think this is helpful for your assignment. Do this part 3. I give you 2 to 3 minutes. You can discuss with your friend. Write down what you want first, and then write down all the definition. Okay? Don't keep thinking, because in the exam, if you stop and think, I think you waste your time. Okay? Most probably you can't get anything, but you need to keep writing. Write down all the definition you need first. By the way, please start preparing your cheat sheet, A4 handwritten. Try to use that to do revision. Okay, make sure it is helpful. Don't copy the whole pages into the exam, then you tell me no use. Okay, so start, do exercises, do revision question using the cheat sheet. Okay, no? Yeah, make your cheat sheet useful to yourself. Okay, it is for you. Okay, to yourself. Make sure it's useful for yourself. So in particular, definition of normal, you want to include into it. Okay, because if you don't know what is normal, then you don't know how to do question.
大嫂，大嫂，大嫂，现在有喝那个维他命 C 吗？没有了，可以去买，附近有沃森。不是，你可以吃一个东西，维他命 B。没有这么累，真的，维他命 B。不要每天吃啦，就是说，来你那天觉得不舒服，就是比较弱一点，你可以吃维他命 B。我妈教我，还是吃维他命 B。那天没有跟我们去吃饭吗？有没？还没有吧？嗯，是啊，上周，上周。
Okay, so how to start here? So you want to show script hash is normal, right? So obviously you should start there. So how do you start? So what do you want to show right now? Always you need to identify what you need to do first. If you don't know what to do, you typically lost. So what does it mean by a normal script hash? So you need to take any hash in this script hash here and any G in your script G there, such that what? Such that the conjugate live in script hash. So again and again, you want to show something in core domain, but your assumption is domain or in domain. So do you have a way to come back or not? Do you have a way to come back from core domain to domain? Do you have a way? Or what way is it? Surjectivity. Because for every surjective means what? For every element in script G, you have a pre-imagined G. Okay, so you can come back there. So you might ask, come back for what? I also don't know. Try first. Okay, we have to try. Okay, because this is the way that we are given to us. So let's do it. So since our phi is surjective, meaning what? There exists a small h and a small g in G. Hey, by the way, can I sit down and write? I think this this table not good. I mean, because of the wire. Wait, let me think. Okay, I'll try here. So you just look at the screen. Okay. So you see, so since phi is a surjective, there exists a small h and g such that what? Such that phi of small h is the script h and phi of little g is the script small g. Right. So I already go back to the normal. I mean, go back to the domain using small h and small g here. But what do we know about our h? What do we know? H is what? There are really only two assumptions here. As h is normal, what do we know? I can try to conjugate my little h here. Okay, if I conjugate it, where should this element live? H again. Okay. But what's our goal? 差不多很像啊，差不多很像 but not quite. So how do we transfer this information? to script H here. Transfer.
How do you type?
How do we transfer here? So again, go back to our goal again， 对不对？我们要从我们的目标出发。So we need to talk about this guy here. So what is this guy already? Now that it has a different face. 的面貌啊 What's the new face for this guy here? We can write it as phi of something. Okay, we can write it as a phi of something. And we write it in this way. So this. But again, by the homomorphism, I can write it as phi of GH, G inverse. But what? But what? But we know that this guy lives in what? Where? Phi of H. But by definition, this is just script H. This is by definition. Okay, so we are done. Okay. Any question? Question? 要拿 inverse 来做。What do you mean? You mean this one equals to what?
那你 inverse H 派我得跑去 H。
No, I mean how do you apply it first? So you inverse the whole thing like this. But like this, it just tells you that it is something inside H. How you gonna play with it? You can apply inverse, but it is just something inside H. So, and then maybe equivalent way to say there's something that you apply by phi, you get GH equals. But what we want is we split it up. We split the H and G up. Usually splitting out is not a good way, but this time we have homomorphism. So if you split it up, you still can combine them together. So this is the power of homomorphism actually. Phi AB equals to phi A times phi B. Okay, so this is a nice thing about homomorphism. Because if you want to talk about maps on product of things, you just tell me how they add on smaller thing. Okay. And also this phi inverse is not sure whether it is homo or not. Last time we proved that it is a homo if phi is isomorphism. But now we only have surjectivity. Not sure we have injectivity or not. In particular, this is, if it's not injective, you cannot just say this is equal to B, you know. Because the inverse image might have more things. So it maybe is a bunch of elements here. So that's why inverse image and inverse function is different. So you want to see this as an inverse image or inverse function. Okay, so there's an ambiguity here. If your function is not injective. So if it is injective, can you do this? You can, but is the inverse function a homomorphism or not? Yeah. I mean, you need to settle this. You need to settle this problem before you can do it. So you need to ask whether the above is equals to a phi inverse of G times phi inverse of H, and then times phi inverse of G. So, is it equal? Okay. Yeah. Only to this stage you can use the normality inside inside your H, right? Okay, if it's not until this stage, then you cannot do anything. Because the normality here require conjugation of elements here. Okay, 3 things get multiplied. Here, the whole thing. So you cannot talk anything about this guy unless you can make it into this form first. If your inverse have a homomorphism property, then you can do it. If not, you cannot. Okay. All right, good. So I think we finished this theorem and then we can take a break from here. So this theorem is quite informative. So maybe please follow it. So this theorem is called correspondence theorem. Okay. So we want what we proven whole in this case here. So meaning we will get a surjective homomorphism first. Okay, let's get a surjective homomorphism. With the kernel K again. We call it K. And then the claim here is, okay, this is a very strong claim. Please follow. This will be your assignment for first question. So there exists a bijective correspondence between subgroups of script G and subgroups of G that contain K. Okay. Right, so let's draw this up. So on one side, you have subgroups G containing K. On the other side, you simply have the subgroup of script G only. Claim here is these are in bijection. Okay, 1-to-1 correspondent here. Okay, so if I draw the notation here, so let's draw all the script hash up. The other side, we have all the subgroup hash. So not all the subgroup hash in the codomain. We only refer to the subgroup that has kernel. Only subgroup hash that contains kernel. So if I want, so if I say that there's a bijective correspondence here, right? So what's the map you can consider? Let's say I give you a hash here, where you should send this hash to. What's the obvious thing to do here? What's the obvious thing? I mean, maybe the script G and G is not the same. So you cannot just do identity. But I tell you a way to go from G to script G, right? Huh? Why got so funny one? So I mean, how you go from G to script G? That's the natural way I told you. You just apply. Fine. Okay. So hash should go to phi hash. Fair enough. Phi hash is already a subgroup, right? We prove a mesh of any subgroup is. But the problem here is how you come back, because there's a bijection. So you should be able to take inverse of this map. So what's the inverse of this map? What do you think? P inverse. Okay, I want to warn you again. Phi inverse. This inverse here is what? It's not a function, it's a preimage. Okay, so here is a preimage. Okay. All right. So not only this, we also have that if H and script H are the corresponding subgroup, so they are corresponding to each other using these two maps here, then H is normal in G if and only if script hash is normal in script G. Okay. Moreover, we know the cardinality. Okay, if they are correspondent again, then what's their cardinality? So we can compute that actually the cardinality of H is script H times K. Okay, the product of the two cardinality. Okay, so there are a few things to do. Okay, so there are a few things to do here. So let's write down the things we need to do and then see how it goes. So let's break this theorem here into a few statements to prove. Okay, let's break it down. Break it down first and then convince ourselves that these are the things we need to do. So, what is the first thing we need to do? Okay, we need to make sure that our phi makes sense here. Okay, our phi makes sense here. H go to phi H. Does phi H live in the set of subgroup or not? Okay, so first thing, we need to prove that phi H is a subgroup of script G. Okay, and then second thing, the inverse subgroup is also a subgroup of G, and it should contain okay, so this first is about the first arrow here, and then second is about the arrow going backward. Okay, so we have proved the not quite right. We haven't proven yet, right? So although we have these two maps, we need to show that it is a bijection. Okay, bijection on subgroup. Okay, bijection on subgroup. So let's phrase this as C. So what do we need to do? If we send the subgroup back to the codomain and then send it to So if we send the subgroup in the codomain back to the domain and then back to codomain, they have to equal to script hash again. And then we need to check the other way around. Okay, so this is the two things we need to check. To get the bijectivity. Okay, to get bijectivity. Okay, so this is very special here. I want to let you see. You see this checking here, right? It's like the what inverse function checking. Okay, it's like an inverse function checking. But this is not true on the element. Okay, it's not true on the element, but it's true on the subgroup. Okay, somehow this inverse image here become a map on subgroup. Okay, becomes a map on subgroup. It's not true element wise. 可以看到嘛，它在那个 element 上面是不对的，不一定对的。Because your function only surjective, not injective. 没有 injective 的话，不一定有某一方面的 inverse， 不一定有。OK， 不一定。OK， in particular, I think 这个应该没有。OK， 你不一定会送回去。如果你是 injective 的话，不 injective 的话，你想想看。And let me finish this in the Mandarin. I will speak in English. Okay, because I want everyone to get this injectivity part correct. So 如果你不 injective 的话， the inverse 里面送去一个地方吧，可能有3个东西被送去同一种东西，但是 inverse 回来你只能够送去一个地方。连其他呢？其他你就永远到不了了。其他你永远到不了，因为你根本都没有送去那些另外2个人，只能够选一个了。啊？没有，记住了哈，记住哈，这样你的感情就是 Yeah. So if you are not if you are not injective, right? Your inverse image, you must make sure you only can send to one of the choice. Okay, you cannot get to the other choice. Once you cannot get to the other choice, this map here can't be this. There cannot be anything always. Okay, so you won't have this left inverse if you are not injective. But in this case here, you see, 看到这个吗? This is really looks like a function, inverse function and function. So meaning what? This inverse image here becomes the function on subgroup. 在 subgroup 上面它看起来像 function. But if you apply to elements wise, not true. This is not true. So this is only true on the subgroup wise. Okay, so very strong statement here. Okay, what else? Then we left with two more things to prove, right? One is about normality, one is about cardinality. So the H is a subgroup, is a normal subgroup of G if and only if P inverse is a subgroup of G. Okay, so D 有印象吗？我们刚刚 prove 了 we just prove D only. Right, we can go front and back, especially when we have a surjective homomorphism. But this is the setting of correspondence theorem here. We have a surjection here. Okay, so we can use what we proved just now. So actually, this guy is already proven. In particular, A is also proven very early on when we talk about homomorphism. And then B is what we discussed just now also. Okay, counted as proven already. So what is not done is the C here. Okay, so this one need to do work. One last thing, okay, before we do work, is we need to prove that the cardinality of H, script H, okay. Sorry, is the cardinality of the normal H. This is defined by the inverse image of script H. Okay, how do you relate this? So this is script H time. Okay. Let's discuss E first. Okay, let's discuss E first. So there are two words here. So 1 and 2. Let's discuss 2 first. I claim that 2 is what we have done before. Okay, 2 is the one that we have done before. How to see this? How to see this? So draw picture again. So let's draw picture again. So you have let's say script H here, and then phi inverse of script H here. Okay, which we call H in this case. What is inside H here? H is a subgroup, right? You should contain identity. And then something else. Again, there's something else. But we know that everything in this subgroup is coming from the pre-image. Okay, so in particular, this E comes from where? And who gets sent to E? The kernel. But kernel is a subgroup inside H. But how about the other elements? How about the other elements? H1, H2, for example. We call them H.
Let's call them H1.
H2, so on. Where are these come from? Where these come from? Huh? Where these come from? Where can these phi 1, phi 2 come from? You take the pre-image. You take pre-image. Okay, you take pre-image. But this pre-image, you can look at who. You can, for example, look at the P inverse of phi I times A. Okay, meaning what? It is a coset. Okay, how about we change color? Yellow comes down where太小了. Let me change color a bit. So, figures of phi y times k. So this guy here, if you send across, you should get this. Okay, but the claim is what? The claim is what? This is the only thing gets sent to H1. Yeah. Okay, so that you can get this equality. It's again like the partition proof. I think you don't believe me. Let me think how to convince you. Okay, so let me show you. Let me convince you. 记得了 ？OK， 最后时间，我们做好这个，我们就可以休息一下，好不好？好啊。Okay, let's convince you how to show this. So, look at phi from this inverse image of script H. Okay, and then this is the thing that we call H. And then this contain K. Okay. Obviously, this is a homomorphism, right? I mean, well, wait, go back a little bit. Let me remind you. So this phi here is going from G to script G. So we just like restrict this part here. It's still a homomorphism. So what? So counting formula or Lagrange theorem tells you what? Lupa, please check. Check. Is it Lagrange theorem or counting formula? Lagrange theorem says what? What? Okay. Okay. I mean by a corollary of Lagrange theorem says what? You can write. So if you have a so let's write like this first. So G is equals to what? The cardinal of G is the kernel of P times image of P. So this is a corollary. So in our case here, where is G, where is curl phi, where is image of P? Where is G here? So okay, so to know these formula here, you need a context, right? You need a phi from G to G prime. Okay, so 对应一下, who should be the G here? We have a homo also. So who should be the G here? Who is it? 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 H. Correct or not? So the cardinality of H is equal to the kernel of phi times the image of phi. But what is the kernel of phi? We call it K, right? Image of phi, we call it what? We call it, if you don't like, we can do phi inverse script H. But we show that it is an identity on H. So it's like this. Okay, so 这个是逻辑，但是你要理解它背后的原因也是一样。Okay, so 这个背后有的原因，为什么合理 ？Why is it true? Okay, this is what we use logic to prove, but you need to figure out why, in principle, it really works. Why it gets split? Okay, using this kernel of K. Okay or not? Does it make sense? Two parts when we do maths it's usually good that you have these two parts here. OK， 逻辑是为了说服人，但是背后的想法是帮你去找新的 idea。Okay, so intuition is for you to work out new maths, but logic is to convince people. Does it make sense? Okay, you have intuition. 很多人很厉害吗？他很厉害的，他觉得哇，这个我会，那个我会，那个会，那个会，这个会，他教不了人的。The logic only works in certain person mind, but can you transfer this logic to others? This is very important. That's why we study logic. OK， 我说啊 ，I say 啊，数学啊是给最笨的人学的，最笨的人学的。Mathematics is for the stupid one, the most stupid one. Why? Because we write everything so clear. You know. In some sense, we are stupid actually. 如果你去啊 I give you an example. If you go to the AI course, SMUM1, I got student in AIT. If you go to their course, their lecturer just put an equation and a picture, and they can say a story already. No definition one. And then somehow the student get it, or they know how to use, or they know how to do. We have to write down everything in detail. 一点都不可以漏掉，漏掉就 blur 了，是不是？ So I say mathematics is the most stupid one to study. So don't think that you are clever, you can't study. Clever people cannot stand mathematics. 太仔细了，因为他们要想很快嘛，他们要想很快的，聪明的人想很快。Alright, so I decide to skip word 1. I ask you to try yourself. So basically, word 1 here is just showing set equality. So why the left element, like everything on the left is in the right and everything in the right is in the left. Okay, so try and do it yourself. Okay, so these two are just set equality. Okay, try to do it yourself. I'll put inside my lecture. Okay, these two are just set equality. Nothing special. Okay, so far, any question here? Any question? Before we finish, not finish, before we take a break, I need to draw this picture for you here. So the picture here is, so after this picture, we will forget about this theorem for 1 hour. So we have a G prime here, okay, script G, and then we have a G here, okay? So what do? You have a surjective homomorphism here. Okay, let's say call it 5. And then what can you do? If you look at all the possible subgroup in G, yeah, H1, let's say H1, okay, so H. Then where are they come from? They are in bijection of subgroup inside your G. So how many of them? 3 of them. Okay, in this case, 3 of them, because they are in bijective correspondence. So we have H1, H2, for example. Okay, 可是 E 不一定要去 E 的，我可以这样子算，我任性的，好不好？Because it's just a bijection, correct or not? So the number might not be equal. Okay. 然后 and then what else? This 3 subgroup here is very special. All of them will contain. Okay. Yeah, so this is the picture that we're trying to get. And then if one of them is normal, use another color. So if one side is normal, the other one has to be normal. If one side is not normal, then the other side also not normal. Okay? Okay or not? Happy? Happy or not? You see, if you see from this picture, meaning what? If you don't know how to study script G, can go and study G. If you don't know how to study G, can go and study script G. Okay. And the information in G can be transferred to script G can transfer to G, G can transfer to script G. Okay, so this is the very important theorem here. Any question before we break? Yeah, any question?
No.
No. Okay. Right. Okay, so let's break until 10:18.
好演吗？我觉得
什么
话题，
啊？哪一个
我说请用话题来表示，你不觉得很喜欢本你？
话题？
我说你都用那个话题来表示，你觉得很野吗？
为什么野吗？
啊？
为什么野吗？
因为很难分啊。
还可以啊，有一个有勾啊，一个没有勾。
但是对于我们这种书写本来就不怎么规范的人来说，就不怎么好分。
确实，但是确实有一个要没有啊，没有。
你要不要干脆到时候 left notes 里面放个字母来表
G prime 你要
对啊，你这个好多吧？
要是我那个孔打进去，
打这个进去，我看一下。
啥？
要自己讲过完了没有？
没有，应该就是跟着这个大体进去。
谁的写的？
啊，这里有 note 吧？
什么课？
然后说你这里招生啊，
差不多。
这里我也玩的，
差不多。
应该是不是到在跟那个学生讲？
对。你有没有打那个什么？哎，我想一下。Every linear transformation 是个 matrix transformation. Linear transformation between finite dimensional space. 有没有那个？
像我们
打那个啊，放那里。我觉得差不多就是这个，但是你去参考一下那本书的 definition，但是差不多就是这个内容，够用了应该。你要会乘就好了，你要会乘啊，
有些人好像看不懂这个，我就这样画出来一点。
可以，对，这个蛮重要。你要会乘，你要会从这边去到这边，都是差不多这样。然后就是这个教你怎样乘哦，教你怎样乘。可能不用这样多计算了，但是就是这个内容。
下个礼拜考试。
有啊，
就那多计算，计算你来对的，
我也没关哦，
是
是我应该也行，应该可以。
到多点再告诉你。
OK。按下我对可以。
让你看。
还好我没有在，还好我及时出去，所以你要跟我讲。我看一下我有没有出去，我不知道有没有。没有啦，顶多可能就给你一个钥匙就行。就没有用办公室台。
蜜蜂在就是广州。
你是需要做纸来拍的？
需要大
正式。
OK。可是不知道里面有一点乱哦。
两个你想？
我两个我想认为。
啊？我想。就是你看多。还是。
他毕业了。
看你发。
我今天要来看一下。
你是
你是要来。
Hello，小杨，洪杰，
下礼拜考试哦。
子明，曾子航，OK。下雨，子谦，李亮，
啊，我连你，我一连嘛，睡觉。
有谦，
我要看自己是不是真的有上课。
Albert，陈斌 ，OK。
有没有去上 PD？
金鱼，超金鱼，
你们
对
昨天可以。
然后又把车动。
超金鱼，哎，金鱼啊，超金鱼，也超金鱼，OK OK。阿瑞，子豪，呀，黑晨 ，OK。何心怡，小月，小月，冰夏狗，
有啊
OK。
下午有补课，谁是阿丽哦？
刘子涵，
你们我下午排。
有
号吗？你的比例下个礼拜。
小贤 OK。方宇，方宇，
要有吗？排起来。
张嘉颖 ，OK。
要回家。
苏瑶，云溪，OK 有看到。
做 MF 啊。
常云，OK。
下午。
延胜，金牌，姚一成狗，一凡狗，一凡。陈平、若曦、赵胜、本秋、赵天、金星、一涵still not here. 一涵 anyone friends of 一涵？
林一航，
user got yes user Rachel got 安心有
不可以，
平安
不
got
可以，
Ian got
你不可以，先不能了，就不要排这边了，我们去。
赵瑞
什么？
金鹏呢？刘金鹏，
反正你讲话本来就小声。
刘金鹏，not here 刘金鹏。
录上前一点，让声音录大一点。
韦哲，哦，并且
我觉得我也生病了。啊，不然怎样？
我自己啊，也不能。
你呀，没给你弄生病掉。你看还你不生病，他是因为什么生病？我是那个seminar过后我就开始不生病了。
哦，就是我那天过后，拜五过后，
拜五晚上就好像有病，然后拜六起来就。
你是爬南东吗？有啊。
我没有。
我们比较严重。
哦，哎，那天一个头一个尾哦，
什么东西哦？
对，做很严那天。没有啦，应该是才诱发了，我觉得。
我们去吃的。
是诱发。
我最近，因为我以为我传染给你。啊？
Ian, where you study before? UEC or foundation? Huh? A level. A level. Where's your A level? Oh, okay. Help university.
啊，HF 是的。
Help. All right. I think we are less people here. Maybe we discuss assignment tonight. 有吗？肚子饿。
我才知道。
Okay, so right. Two, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Okay. So now I will continue with finitely generated abelian group. Do you know what does it mean by all these words? So you need to decode the word bit by bit. So what does abelian mean? Quantitative, right? Okay, x, y equal to y, x. What does finitely generated mean? Generated means what? Something, all the elements inside your abelian group can be generated by some generators. But finitely means what? The generators are finite. Okay, you just only need finitely many things to build up your abelian group. But you know that one group is finitely generated abelian group, right? What is that group? Only cyclic group. Which one? Okay, so all the cyclic group is finitely generated. Very good. I mean, if you have yeah, right, correct, all of them because built up by one. But there's one specific group that you should know. You see it during your kindergarten or not yet? Primary. Hey, primary share negative 嘛？还没有不是 ？Okay, secondary. Huh? I give you hint already. Negative got negative one. Once the group is a finitely generated abelian group. Yeah, integer generated by what in particular? Yeah, you generate by just one. One. 一个一吧。Okay, use one to generate everything. Infinite things there. Yeah. So how can you get all of them from one? Okay, so now we will introduce a more general stuff, which is called the Cartesian product. Okay, I think you know Cartesian product, right? R2, R3, R4, something like that. But now we're gonna introduce Cartesian product of set. Okay, more general a bit. So we just look at a random set. Okay, we look at a random set. Let's call it B1 up to Bn here. So this is a Cartesian product of n set. Okay, n of them. Is again a set. Okay, again a set. So if it is set, right, I need to tell you how the elements looks like. So what are the elements here? The elements are the n tuples. Okay, so B1, B2, until Bn, such that where these Bi live, these Bi I should take from our set. Okay, take from our set. So in this case here, we will denote by B1 cross B2 cross cross Bn. Okay. Or we just write it in the product, big product sign. So you see, this Cartesian product set is a set. But this is not always true. If you think of it, if you want to take infinite product, how do you do it? Okay, we won't define it as a set already. We'll define it as a function. Okay, if it's infinite. You will see this if you go general topology. Okay, infinite product, Cartesian product of infinite set. But it is finite, still finite set that you take product with, you still can write it as a set. Correct or not? What's the element in R2? What's an element in R2? What's an element in R2? Can you give me one element in R2? 什么 the sorry coordinate. What sort of coordinate you can get? Huh? What's the element in R2? Element in R2. Just hello. 哎，理一下我，理一下我，很可怜的。R2 里面的 element 有什么？ Sorry? Yeah, can you give me a specific point? 0, 0, the origin in particular. What else? 1, 2, 3, 4. Half, half. 4, 3. Why you can pick this point? The first coordinate live in R. The second coordinate also live in R. So you can take pi also can. Pi e also can. Pi half also can. Okay, as long as they are coming from the corresponding set there. Okay, so in particular, what are the set we are interested in? Just now we talked about cyclic group, right? So we can talk about, let's say, Z2 cross Z3, or Z2 cross Z2, right? Or even we can take Z cross a matrix group. Okay. We can cross everything with that as long as it's a set. Okay. So when we put cross here, why we put cross here? Really, there's like a multiplication structure there. Okay, later we'll see more about this set. Then you'll see that there's really some multiplication structure there. Okay, so we really think of them as a multiplication. Okay, so if you multiply two numbers together, you get another number. That's similar here. You multiply n set together, you get another set. Okay, it's still a set. You multiply set together, you still get a set. Okay, so it's similar. It's really similar. Right. So, what are elements here? So, for example, in the first case here, we could have 1, 2, for example. And in the other case, we can find 1, 1. Last one, I mentioned, try 1 and then what's an element in GL2? 1, 0, 0, 1. Good. So this is the identity element. Okay. So make sure you know what's the definition of this set. So this is a invertible 2 by 2 matrix. Okay. So don't choose non-invertible one. Right. So in this class, if it is not a group, we don't want to study because this is a class about group theory. So the theorem was if, so suppose GI, so let's say G1 up to Gn are groups, then our claim is the product set of G1 up to Gn is also a group. So to be a group, what do I need to tell you? I need to tell you the L or C. So can you think of a possible L or C here? So I give you two elements inside this. Let's do proof. So if I give you two elements inside this product set, let's call it what? Let's say G1, G2, G3, until Gn. And then let's say 1, F2, F3, until Fn. So how to compose them? How do you define? What's the natural way to put them together? 来，嘉玲 How to put them together? 相乘在一起，这两串东西，两边都有 n 个东西，相乘在一起。 讲一个方法一下，我给你自由发挥。哎，两边都有 n 个东西。谁跟我讲，不要跟子轩讲，跟我讲。D1 乘 F1 加，然后so everyone got his her logic or not? Logic, huh? Okay. So you ask you a question first. What your LLC have to do? You have to go back to this group, this set here. But the element in this set looks like n tuple. If you make it this way, become what? One tuple. 你没有回去啊，你跑出去了。所以我要的 so what kind of answer I want? I still need a n tuples here. So how to create another n tuples? 要不要再 try 一次？跟我讲过嘛？要有 n tuples， 所以要不要再 try 一次？ So here I say not n tuples because only one tuples. 要不要再试一次 ？OK， 给别人机会，就是子轩啦。来试一下 how to get another n tuples。有吗？有方法吗？讲一下。不要太复杂啊。对。嘉玲来 Q 另外一个嘉玲。可以。还答对有5块钱。OK， 来。OK， 谁要帮忙？还有若星，你要帮忙吗？加号变成逗号，这样是吗？如果加号变成逗号 ，so meaning we just take G1 F1, G2 F2 until Gn Fn. Okay. Possible? Maybe possible. So you just need to check that whether it is a group or not. Okay, whether is it a group or not. Is it associative? To prove associative, what you need to do? You need to take 3 n tuples and then check that if it is associative. What do we say here? We multiply components wise. 第一个跟第一个乘，第二跟第二乘，第三跟第三。Component wise. You n 个 component. There's n components here. So you multiply component wise. Okay, so you need to, if you want to check associativity, meaning you need to check what? If it is associative components wise. Is it associative or not? Associative, right? Because each of the group that you multiply here has associative L or C. Identity? Who is the identity here? 1 in all spot. So you just pick all the identity in your group, put them together. N identity of them. Okay. Inverses, similar. Because we define it component wise. So components wise, you should have inverse. Okay. Because in every component, they are already grouped. Okay. So what we do is just we put them together. Okay. Any question? Try and write it out yourself. Try and write it out yourself at home. Okay. 有问题吗? Any question? Then before you try at home, you must get what I said first. 问题？有问题吗？问题有问题要问出来啊，问题不大。 可以吗？问题，有问题吗？你们三个？没问题吗？我看你们一直睡觉啊，有问题要问啊。All right, so wait, we have a LOC, associative LOC. Because each GI has associate LOC. Okay, so what's the identity here? So identity here is just you take identity in every spot. Okay, so what's the inverse here? So the inverse of an n tuples, the n tuples of inverses. So you just take inverses in every spot. Okay, component wise. I cannot understand what I say. So for example here, let's give you an example for this to imagine here. So let's say G1, G2 is equal. I mean the inverse of this tuple is what? It's simply G1 inverse, comma, G2 inverse. Okay, so how to check this? How to check? You also use my LOC to check it. Okay, use my LOC to check it. So is it true that G1, G inverse is identity, and then G2, G inverse is identity? Because this is how we get our identity. Okay, right. So remark. So if the LOC of each GI is commutative, then we will write the big product of GI as the direct sum. Okay. So this is called the direct sum. Okay, just a notation for a moment, because I think we won't deal a lot with direct sum in this class. But for this purpose of this class, if you see this direct sum, meaning all the LOC is commutative, abelian. Okay, the whole thing is abelian. Right. Okay. Okay, so far so good. This is how you do R2 computation, right? How you add 2 points in R2? Also component wise. You also add component wise. This is what you did in calculus also. Okay, if you want to add 2 vectors together. Okay. Okay, next. Next, I want to look at some example is when does the product group is cyclic? Okay, in particular, we look at some easy example first. So for example, Z2 cross Z3. Okay, and then the other example is Z2 cross Z2. Okay, I'll let you think a bit. Which of them is cyclic? Okay, if it is cyclic, what is the element that generated? Try and error. Try now. Write it down. Okay. So the question is, so let me write down the question. So we know that they are grouped already, right? So which are the following groups? Which are the following groups cyclic? Cyclic means what? You are generated by one thing. So can you use one thing and keep adding to itself to get the whole group? Okay. Is it possible or not? Try. Okay, you have to try that. Now. So the LOC component Y is addition. Okay. So let's write down what's in this set here. So we got a 0, 0, 1, 0, 0, 1. No, let's write down all the. Okay, I think I got a way to write it down. So write 0, 1. This way, maybe use 1, 1. Zero, 0. Okay. Do you guys know how to compute the whole cardinality or not? Which one? Do you know how to compute? So in the first coordinate, you have 2 things, right? Second coordinate, you have 3 things. So in total, you could have how many possibilities? 3 times 6. Because we consider all the possibilities. So meaning the cardinality of a product of group is the product of cardinality of the groups. Okay, so have you tried out which one is cyclic? Which one is cyclic?谁是 cyclic？ 哪一个？第一个，子涵，你说哪一个？第二个也 cyclic。If 第二个 is cyclic, you need to tell me who is the generator. Who is the generator? Okay. 康平说第一个是 cyclic. You have to tell me who is the generator. 一二 ，OK， 一二。那个呢？子涵呢？Okay, let's try. Let's try. So cyclic means what? If you keep adding to yourself, you should get everything. We try. Okay, let's try. So 1, 2 obviously is there. So 1, 2 plus 1, 2 is what? 2, 2, 4, which is equal to 2, 1 in our case because we are mod 3. Okay, so 2, 1. And then if you add to 3 times it, 谁是0啊？ 2也是0, right? So because we are mod 2 in our case, right? Mod 2 and mod 3. So if you add 1, 2 again to it, what do you get? 1, 3, which is 1, 0, because mod 3. Okay. Again, if we add again, 2, 2. But 2 in the first spot is mod 2. So you get 0, 2. Can we do it again? 5th time, eh? 1, 0. Okay. 1, 1, eh? 1, 1, right? Because 1, 4. 1, 4, 4 mod 3 is 1. Okay. Keep going on. If we go on, what do we get? We get 2, 2, 3, which is, 2, 3, which is 0, 0. Okay, so you see, we get everything right here. 6 of them. How about 1, 1 on the other side? 1, 1. 1, 1 plus 1, 1, you get what? 0, 0 already. So you will keep the cycle already. 1, 1, 0, 1, 1, 0. But how many things inside here? We got 4 things there. So we can never reach 0, 1 and 1, 1. Sorry, 0, 1. Which one cannot reach? 0, 1 and 1, 0. But maybe you can say, how about what if 1, 0 and 0, 1 can generate? Go and try. 1, 1 plus 1, 1 is what? Again, 0. 0, 1, 0, 1. Again, 0. So meaning what? These 3 elements are order 2. But you have 4 order 4 inside your group is order 4. So you cannot use element with smaller order to generate your group. Okay. Because there's no chance to reach the other elements. Because you already go to identity earlier. This is not cyclic. Not cyclic. You can see that. What can you observe here? So actually, you observe that non-trivial elements, non-trivial order 2 only, which is less than the order of the group, which is less the order of. Does that make sense? Question? Okay, less than the order of the group, so you cannot have chance to meet other friend inside your group. Okay. 有问题吗？哪里 ？order 什么？哦 other 啊。Okay, sorry. Order. Right. Okay, we still have 5 more minutes, so let's finish this theorem. So let's give a theorem here. So how do we decide? So the theorem is Zm cross Zn. Okay, the group Zm cross Zn is cyclic. If it is cyclic, it will be isomorphic to. It will be isomorphic to Z of m times n. Okay. Just now I told you, right? What's the cardinality of Zm cross Zn? You just had m times n. Then this guy also have cardinality m times n. Then you might, I want to ask whether these two are the same or not. Yeah, they are the same up to isomorphism. Because they cannot be equal. Because these two is really different. One is 2 tuple, one is 1 tuple. Cannot be the same. But they can be isomorphic. Meaning the way they multiply is the same. Okay. If and only if what? Okay, if and only if m and n are relatively prime. So we bring in the idea of a number theory here. So relatively prime. That is, the GCD is equals to 1. GCD. Okay, let's look at our case here. Correct or not? You see, 2 and 3, the GCD is 1. But 2 and 2, the GCD is. Yeah, so let's quickly prove this. Let's prove it. Which direction you want first? Left to right or right to left? Left to right, Okay, let's do left to right first. So let's assume we know that it is cyclic first. So in this direction, we will prove by contrapositive. Meaning, if we know that the GCD is not 1, then we want to show that it is not cyclic. Okay, if it's not cyclic, then obviously cannot even isomorphic to ZMN because ZMN is cyclic. Right, so prove by contrapositive. So suppose that our GCD is greater than 1. Okay, if it's greater than 1, then you can look at the trick here. So whenever we talk about GCD, we want to take this number, divide Mn. Because it is their common divisor. So we can do this. If we do this, obviously, this is still a positive number. It's still a positive number, positive integer, because m and n already positive, and then d is also positive, so this whole thing is positive. And it is an integer, okay, not fraction. It can be divisible because GCD is a common divisor. Okay, because since d will divide both m and n. Okay, so consequently, what? So here is the big claim here. So here's the big claim. So consequently, it's like what we did our in calculation just now. So let's look at this big claim. So let me write it as a claim here. Then we will think about for a second. What do we have? For all Rx in our group, if you add them, so let's write this. So if you add them, mn plus over d times, it will be 0. 来想一下为什么对 Let's think why is it correct? Is it correct? Why? Why? Okay, this is a very 很有智慧的算法在这里，非常有智慧。A lot of wisdom here. It's very wise, this calculation. 想一下 to be equal to 0, 0, how to equal 0 on the first part? Mod m. Second, mod n. So do we have mr or not? Multiple m of r or not? Do we have it? Why? Sorry? 我猜 mn， 但是还有一个 d 在这边搞事情哦，这个 d。如果是 mn， 我就开心了。但是还有一个 d 在那边搞事情嘛？他真的是在搞事情吗？还是他是一个天使？其实有没有 ？Does this d helping you or not? D can divide n. So m. So okay. So for this r, right, you can see mn over d as m times n over d. But n over d is still a integer. Okay, so meaning you already add r n multiple times. Agree, ma? So meaning on the first spot, we should get 0. Second spot, what do you mean by same? 讲看，哪一个？他没有讲。讲看 ，why second spot is similar? 啊 ？n times， but 还有一个 d 哦，是不是搞事情？这个 d， 他是天使 ，why 是天使 ？Because d also divide n， 他跑去 n 那里了。Okay, so m over d times n. Okay or not? So we see this number in two ways. Okay, one is multiple of n, one is multiple of n. But after we got this equal to 0 means what? 每一个东西的 order 都小于 n。像我们刚才讲 order 2 element 是造不出其他的东西，因为你最多只会遇到 mn over d 的 element 罢了，每一个。所以你自己一个人是做不完全部的。Okay, so one element cannot generate your group because their order is less than n times n. 对吗？我们的 statement 要 prove 什么 ？It is isomorphic to z 乘 mn。还有呢 ，what is the cardinality of zn cross zn？ m 乘 n， 遇不到这么多人。OK 了 ？Hence, so hence, there's no elements, okay, Rx in Zm or Zn can generate the entire group. Because if you take any elements, okay, and multiply to itself multiple times, at most mn over d, you should get to identity. So there are how many elements that you cannot reach? So let me make a remark here. So we see that you can't produce the other How many elements of them? Mn minus Mn over D. If you want to simplify it, it's just Mn times 1 minus D. 1 minus 1 over D. Okay, so you cannot reach all these. So meaning you cannot generate the entire group. So no, you can generate the entire group. So what? So Zm cross Zn is not cyclic. Okay, if it's not cyclic, then it won't be isomorphic to Zmn. Okay, because Zmn obviously is isomorphic. Okay. Any question? Bye-bye. Question? Any question? Last question before we finish. The other direction, I think we left 2 to 9. Any question before we finish? Okay, if no question, there will be still office hour this afternoon if you want to come. And then tonight we have class. See you later.